Hi, in this second organic synthesis video, I'm going to talk about the synthetic route of dihydrobocconine. Dihydrobocconine is a benzophenanthridine alkaloid that is extracted from plants primarily found in the middle and lower basins of the Yangtze River. There are more than 100 alkaloids found in this family of compounds, and these compounds have a variety of important biological activities which include anti-cancer, anti-inflammatory, bactericidal, and growth promotion activities. So similarly to my previous video, I'm going to skip through the content that's not relevant to the topics covered within the last few weeks of CHE302U. So the first relevant reaction is the reaction of this alkyne with this organic iodide via the Sonogashira coupling mechanism, which involves both palladium and copper catalysis. This is a general overview of the reaction where we use bis-triphenylphosphine palladium-2 dichloride as the palladium catalyst source in THF as the inert solvent. Palladium catalysis primarily works by exchanging between the 0 and +2 oxidation states. So firstly, we want to reduce the palladium-2 that we have here into palladium-0. So to do this, we would have a triethylamine molecule attack the palladium, kicking off a chloride ligand. The new triethylamine ligand is subjected to beta hydride elimination, which leaves behind a hydrogen on the palladium. This is perfect, as the H and Cl can be eliminated off together to give us the palladium-0 species bis-triphenylphosphine palladium-0. We can use this species in the catalytic cycle. This is the catalytic cycle of the Sonogashira coupling reaction. We start with this palladium-0 species, which we've just generated, which undergoes oxidative addition with this organic iodide. The palladium-0 will be oxidized back into palladium-2, which then undergoes transmetallation with this alkynyl copper, so that the alkynyl species is transferred onto the palladium. The alkynyl copper species that we used in the transmetallation step is generated by reacting this initial reactant alkyne with copper iodide and this triethylamine as the base. Copper is catalyzing this reaction in its own smaller catalytic cycle. So this molecule does not have the right stereochemistry for the reductive elimination yet. So it would undergo trans-cis isomerism so that the two R groups would be cis to one another so that they can undergo reductive elimination to form this product. This is the product of the Sonogashira coupling, and the palladium-0 species would be regenerated to continue the cycle again. The next step that we're covering is the Ullmann reaction. The intention of this step is to aminate the molecule by replacing the iodide group with the methylamine. While it's possible to do this reaction by the Buchwald-Hartig amination reaction, as we do not have a palladium catalyst or phosphine ligands, but do instead have a copper catalyst, what we can do is the Ullmann reaction instead, which gives similar results. So firstly, the copper bit is a bit different from palladium, where palladium likes to switch between the 0 and +2 oxidation states. Copper prefers to switch between +1 and +2 oxidation states instead, but can also go to +3, with +3 being a bit rarer and harder to observe, but is definitely known to exist. So we firstly need to generate a copper-1 species from our copper-0 powder. We can do this by the homocoupling of two organic iodide species. The oxidative addition of the organic iodide species to the copper results in this copper-2 species being formed. Copper powder can reduce this copper complex, while itself becoming oxidized into copper iodide. Now, taking a molecule of the initial organic iodide species, if we do another oxidative addition, we get a complex where following reductive elimination, we get this homocoupled species and copper iodide. While the homocoupled product generated is a waste product, the amount of waste product produced will be relatively small, considering that once the copper iodide is generated, the catalytic cycle will work much faster to convert the remaining copper powder into copper iodide than the homocoupling reaction can. So we end up with a small amount of homocoupled waste product. Ultimately, it doesn't cause a huge yield issue, as we still get 72% yield from this reaction. So now that we have prepared our catalyst, copper iodide, we can move on to the catalytic cycle. Starting with our copper iodide, reacting with our methylamine here. Both are reduced by ethanol, which acts as a mild base in water. This copper amine species, which we've just generated, undergoes oxidative addition with this organic iodide, forming this complex. The amine and aryl substituents will be eliminated together to form the product of the Ullmann coupling reaction, and the copper iodide species is regenerated. The last step is the intramolecular Mannich reaction. This is the intramolecular Mannich reaction. Here we want to make a ring between this amine and this anisole-like ring here. We do this under a nitrogen environment to prevent oxidation of the amine into an aminium, because in the presence of oxygen we would produce bocconine instead of dihydrobocconine. The first reaction is the use of trifluoroacetic acid and paraformaldehyde, which acts similarly to formaldehyde, to turn the amine into an aminium. The lone pair on the ether will then shift electron density towards the aminium to turn it back into an amine. This ring-forming step is finished after this hydrogen is kicked off of this carbon, which is bonded to the nitrogen. This shifts electron density back, allowing the carbonyl to regenerate back into an ether. The final product of this reaction is dihydrobocconine, which is the target of this synthesis.